Alright, so let's talk a little bit about arc length. So this is just the length of a curve in M, although really we can just think about, since our surfaces M are in R3, we can think about this as just a curve in R3. So how can we find the length? So for the length, what we can do is just pick a partition of our time interval, see where these points get mapped to, and just compute the length of the segments between the points. So remember I mentioned earlier that this was a bad way to do it for the surface. However, in one dimension, this will work out just fine if we do it for lengths. So the lengths will converge to what we should consider the length. Alright, so really all we just compute, so the formula is pretty easy. So we have the length of gamma at ti minus gamma at ti minus 1. And if you use the mean value theorem, you can kind of rewrite this as a derivative. Okay, so we have the formula for the length is this. So you can think of this as a theorem. This time is actually a theorem, not a definition, because we can actually start with the definition as coming from this, and then use the mean value theorem to prove it. Okay, so notice that this funky term pops up, so you've probably recognized that. It showed up in a lot of our calculations. It showed up in our surfaces of revolution calculations. So, and that's not a surprise. That's because if I view a surface of revolution in the right way, so let me draw maybe a piece of one over here. Okay, well, we have the arc length hiding right up here. So you can think of this as the length of the curve and then times 2 pi. So the length over here. So this is kind of another somewhat instance of Pappus's theorem again. Alright, so let's look at, you've probably seen this before, but I like doing little demos. So here was that 2 plus cosine of x, and if you try to compute the arc length, you'll run into the same trouble as computing the surface area. You're going to get an elliptic integral. So if you're interested, you can actually look at the code. It's not very difficult to come up with this plot, and as you do more and more lengths, it'll fit the curve very, very nicely, and this will compute the arc length using this. So let's actually make it smaller so that we can see the line segments as they approximate. Okay, so if I do 5, it's pretty rough, but even at like 24, they align pretty nicely. Alright, so what else do I want to say? So this is kind of stuff I couldn't quite fit into the regular flow of the presentation. However, I thought it was just super cool. I want to draw to your attention to this little piece. It looks kind of like a lipstick. So there's this kind of old way of writing the formula for the surface area. So I wrote it as the cross product of these two vectors. However, you can write that as the secant of theta. And well, I'll leave it as an exercise for you to convince yourself why that makes sense. And the picture I like is actually down here. If you visualize it in this little way, hopefully just thinking about how a square in the plane, if you kind of tilt it at an angle and look at the projection of the ramp onto the square, you can kind of convince yourself where the secant will come up. So I don't want to spoil it for you. I'll leave that as something for you to do. And the other thing I really wanted to talk about was, well, how do you generalize to higher dimensions? There's a reason why I like writing the formula as the square root of the determinant. It's because of the change of variables formula. So if you go to higher dimension, well, you can compute the volume of a cube or a parallelepiped in R3. And if you want to see how it changes under a linear transformation, well, it's going to be the determinant of a linear transformation is going to change, let's say the unit cube into some parallelepiped, and the absolute value of that. So we actually have to worry about the order of the vectors, but that's an entirely different lesson. that I don't want to get into. But anyways, those are the last couple remarks, mostly this really cool alternative derivation of theta. All right, so there you have it. That is my talk on surface areas and wormholes. Thanks so much for listening. In the next video, I'll talk a little bit about myself doing some Q&A for the Interesting Talks series.